So, hi everybody. Uh, I can't see anything about you, but I assume you're listening. My name is Denis. I work for Bloomberg, which has absolutely nothing to do with my talk called My First SIMD, implementing STL algorithms using AVX2 extensions. If you want to follow along for some reason on your laptop or something, here's the link to slides, or I also posted the slides in the general chat. Generally speaking, what's this about, right? I had seen a ton of talks about SIMD, and they were quite good talks, right? But the problem I had is when it comes to algorithms, they were like, and this is how we implement SUXP. And if your data is completely aligned, and if your size is divisible by the size of the register, and I'm like, SUXP is great and all, but on one hand, there exists like C-string library, for example. And C-string library requires none of those things, right? It is completely SIMD optimized. On the other hand, we have things like, stud_unseek in C++20, which is supposed to have vectorized sort. And how can vectorized sort work? So I decided to find out, spend a ton of time on Stack Overflow, implemented a bunch of code, carefully measured, and now I'm going to tell you what I learned. What's the point of all of this? Right. So this is on my machine, comparison of this strlen versus, while not 0 ++, right? And we can see that for 40 bytes, for 40 characters, we have about strlen is about 9 times faster. And if we go to bigger sizes, not that it's super relevant for strlen, but still, right? What's this difference? It's about 30 times. Strlen is about 30 times faster than your scalar loop. And the same goes for 10,000 characters. And we want to do that. We would like to utilize that power in our own code. A few disclaimers, right? First of all, I'm not an expert in SIMD. I talked to some people who know what they're doing, and I asked a bunch of questions, and they reviewed some of this. So I'm pretty sure I'm not telling complete nonsense, but still beware. I tested everything on one compiler and one machine. So it's Clunk built from Trank, right, a few months back, and it's Intel 9070. So it's a reasonably recent home PC, right? Everything is kind of x86 specific. There are equivalent things on ARM and Power, but I don't really know them. Right? So expect everything to be x86 more specific. And finally, I say things, but they're mostly opinions than fact-based truth, right? So take it with a grain of salt. The overall plan of the talk. First of all, I'm going to explain, hey, what is SIMD and how do you get it, right, in your code? Then we're going to dive into strlen, and we're going to learn, most of the things there are to learn about strlen. Hopefully, by the end of this talk, you can write one. And finally, we're going to look at some other algorithms on a very high level, right? So that you can understand what are other things possible with SIMD. Okay, what's SIMD and how do you get it? Right. Basically, SIMD stands for single instruction, multiple data. And there are a lot of things that kind of fall under that category. GPUs, for instance. GPUs are definitely SIMD. But we're not talking about GPUs. What we're talking about is your regular CPU have some SIMD capabilities in them and has ability to execute the same instruction on multiple elements at once. So these things are extensions, right? And this is one of the important things to understand about SIMD is that a compiler by default will not just generate this SIMD fancy instructions. You need to tell it what processor you have or the minimum processors that you have. So you need to understand what are the families of SIMD extensions for it. It's the first group is SEC 1 to 3. I group them all together, and they're really old. For example, when I was a kid, everybody wanted to play video games on Pentium 4. Right, and Pentium 4 already supported SEC 3. And we have SEC 4, SSE 4.2, AVX. AVX is available, for example, in PS4. For those of you who don't play games, it's a last generation console. It's about 6 years old, and it didn't have the top hardware back then, right? AVX2, this is the one we're targeting, and it's still pretty old. Like, for example, most of my slides I did on this MacBook Air from 2015. Right, so it's a MacBook Air, not top-of-the-line processors, nothing, like, 5 years old, supports IVX2. And finally, nowadays there's IVX 512. It says on my slides that it's servers only. It's not technically true. There is already something for home you can buy that has IVX 512 capabilities, but still, for most part, it's fancy, cool servers. So again, we're targeting IVX2. So the first thing you need to do after you kind of understand what you're targeting is you need to tell your compiler about it, right? In my case, it's very simple. I am building and running on the same machine. So I just say March native and everything works. You can compile for specific architectures. You have some minimum requirements, you can compile for that. Or you can compile for a few ones. And finally, what you can do is you kind of can compile, for example, a DLL in a few different modes and select one in runtime, but it is difficult. So specifically not to get into ODR violations, right? Because you're trying to compile the same functions into multiple different modes. This is scary stuff, but some people manage to do it if you really need it. So, okay. After we told our compiler we need to get some SIMD code, right? There are a few ways you can do it. The simplest one is using auto-vectorization. Basically, you write your scalar code, and compiler can, transform it into fast SIMD code. It's really cool. The problem is it's very limited. Basically, from my experimentations, what I can see is that compiler can do anything that looks like a transform or anything that looks like a transform reduce. Right. This is a quite wide category of algorithms. So, for example, stud adjacent difference gets vectorized. You can take a stud reduce, plug in, a minimum there, and get the minimum value out of an array in a vectorized fashion. Right. Really cool. Second thing, there are pragma-based approaches like OpenMP. I tried a little bit, failed miserably. However, I know that the only existing implementation of stud-unseek, right, the standard vectorized algorithms, uses some sort of pragma, some sort of OpenMP with extensions. So people kind of use it somehow. And finally, what we can do is we can write it by hand using intrinsics or assembly, right? This is kind of what we're doing, right, for the most part. Okay, for the first two approaches with auto-vectorization or OpenMP, it's magic, like you don't care. But as soon as you want to go to intrinsics, you need to understand what is a programming model that's like processor SIMD implies. Here's kind of how it works. You have like super wide registers. On IVX2, which is the one we're doing, it's 32-byte registers. All right, and I can do a lot of things with the 32-byte registers. I can interpret it as different types. Like I can say that it's going to be 32 chars, or 16 shorts, or 8 ints. I can do floating point, no problem, right? Then I have a bunch of operations. Here I highlighted like a few additions with, like this is add chars, add shorts, add ints, written with intrinsics. And you got to understand a little bit about these intrinsic things. Like, first of all, they're very much not complete, right? You can have some operation defined for signed numbers, but not for unsigned numbers, right? And the second thing, like, they can be very specific. Like, you look at an instruction and it says that it does something, you're like, what the hell is that? But how well you can use these intrinsics to get what you want is effectively defines how well you are a SIMD programmer, like at least in big part. It reminded a lot of like template metaprogramming when you would use initializer lists to iterate over types in a type list. right? Initialize a list is very much not designed for it, but you can kind of make it work. Same principle with SIMD code, right? Few things on using intrinsics directly, right? Generally speaking, you just include this header, emintrin.h, and you're good, right? You can write intrinsic code. There is into intrinsic guide, which is a, all of the instructions for x86 listed out with some documentation too. However, it is really painful to use them directly. I seriously recommend you wrap them into some sort of library that provides a nicer API. And generally speaking, you don't really have to do it yourself, right? There are already a bunch of libraries like this. I seriously recommend this Jefferson Amsmooth stock from CPPCon 2018, where he talks about libraries like this and what you can do with them. I was looking for a library like it, and I was interested in three things. First of all, I needed a documentation, so a complete list of everything that library can do. Effectively, a library like this is a collection of tricks, right? We can do this with SIMD registers, and we can do this with SIMD registers. So I need just a list of everything, right? Second thing I really wanted is extensibility, right? Basically, a library has some tricks. I need some other tricks that they don't do. I need to be able to write them and somehow integrate them into a library without pain and suffering. To emphasize how important extensibility is, none of the algorithms I'm going to show are completely writable in the library I'm using. Right, so I had to write some intrinsic code directly for all of them. And finally, I was looking for type support. I wanted to write strlen, and some libraries didn't support chars. So, okay, I looked at NSIMD, TSIMD, XSIMD, VC. For some reason, they didn't work for me, at the time at least. I started writing my own, which was a super useful experience for me. I learned a ton, but finally, I settled on Eve. Eve is this new library developed by Joël Falco, and it's kind of does everything I needed. Okay, and with this, I'm ready to jump into strlen. Right? What's the problem with strlen? Right? Basically, we want to be able to load 32 bytes and do something with them, but the whole point of strlen is we don't know how much space we have. We don't know how long our string is, so we don't know if we even can load 32 bytes. Here we need two things. First of all, we need to know that allocation happens in pages, meaning that if you have 1 byte of memory somewhere, it means that you have the whole page to yourself. You don't know what's there, but it is for your process. And the second thing we need to understand is that align addresses are safe. Let me show you what I mean. So let's say this is my page, and this is my string somewhere on that page, right? Let's put addresses on the thing. So this is the beginning of the page, end of the page, and the string. And the beginning and the end of the page, they will be aligned to the size of the page. In my case, and by default, the smallest one is 4 kilobytes, right? Let me align S, right? Basically, let me strip off some bits on the end, right, and make it an align address to 32 bytes. What do I know about this? So first of all, this is the closest address to S that is aligned to 32 bytes. It means it's going to land on the page because the beginning of the page is aligned to 32 bytes. And the second thing I know is that because everything is aligned to 32 bytes, this distance is divisible by 32. And what I can do is if I can load by 32 bytes 1, 32 bytes 2, 32 bytes 3, I'm guaranteed to end up exactly in the end of the page. I'm not going to read someplace over here and trigger, processor interrupt or anything. I'm safe as long as I'm reading from aligned addresses. Or if the string continues on the next page, I'm still good. This is my string. The next page is also mine. It takes a little bit of think about. I will leave you to it afterwards. So, okay. Let's say this is my string. I removed everything about pages. What I can do is I can align my address of string, and I can load 32 bytes from there. Right. Then I have this primitive, even with intrinsic, that is really fast, called first true, right? And what it does, it like, hey, if there is any zeros, it will return me the position of that zero. Well, kind of. And if there are no zeros, it will return me null. I have a little bit of a problem that if I have a zero here before my string s, I don't know what's there, right? Then basically my strlen will not work. So first true accepts this ignore parameter that allows me to specify, hey, I want to skip everything in the beginning. So cool. In this case, I'm going to ask like first true ignore, no zeros found. First true ignore, no zeros. Boom. Come on. Found a zero. This is my answer. Okay, let's look at the code. Like this is my strlen, it accepts a string, returns a size. First thing I'm going to do is I'm going to declare this type def void for if void of char, right? This if void of char is this abstraction on top of a register. In my case, this is going to be like a register of 32 chars, right? If it want to be a different platform, it could be 16 chars or 64 chars, but in my case, this is 32. I need some zeros. So I'm going to create some zeros. And OK, first, as we discussed, I need to align address of s. This is my aligned s. And I use this function previous aligned address to 32 bytes. And then I'm going to load my 32 bytes from there. I need to test that first registers that I loaded. Everything between s and align s has to be ignored, as was discussed. And so there is this object, there's this type ignore first to do it. And then, I'm going to try to find a match using my first true primitive. Like this car equals 0 is probably the most controversial aspect of the interface of the library, but it's actually common between all of those libraries. Basically, it will not return you like one Boolean saying, hey, are zeros equal or not? It will return you like a register of 32 Booleans, right? So, yeah, and then first true will find the first one that was, true. Okay, and while I didn't find any zeros, I'm going to continue forward and test all of the elements against zeros. And, after the first register, there is nothing to ignore, so I'm going to ignore none. And finally, I have to do some computation to, hey, where I am, where I stopped. This is all cool and all. However, I have a problem. My problem is dynamic analysis, right? Like, your processor knows that you're allocating pages. Your operating system knows that you're allocating pages. C++ doesn't know anything about pages. So basically, dynamic analysis, if it sees you loading, something you didn't allocate, it will object. In general, they're working on it. Like, if you load a register, but you didn't use some of it or something, there is some work being done like that. But for now, I can help you in case of Clang. There's this function called load unsafe. It's the same load. The only thing, it has like a special attributes on it, like no sanitized address, for example, to say to other sanitizers that, hey, we're doing something weird here. And so address sanitizer will work with our strlen if we use this function. I'm going to leave you to meditate on the implementation for a little bit. Just so it can sink in. Okay. Again, the slides are posted, and so you can look at it afterwards as well. Measuring. SIMD is an optimization, right? So we want to measure how fast it is. Or like really simply, like I'm using Google Benchmark. I have some ways that is really complicated to deal with code alignment issues. Here's the thing, like I'm measuring like 40 bytes, 1,000 bytes, and 10,000 bytes. Usually when you measure an algorithm, you measure like in the number of elements. And for example, on my machine, sorting 64-bit numbers is faster than sorting 32-bit numbers, right? Just for some processor reasons. However, for SIMD, this is never the case. Basically, you operate on these 32-byte registers, right? And SIMD in many respects doesn't care what's in them, like it's a chars or it's ins or whatever. Which leads to a nice optimization trick where if you can pack more data, if you can use smaller types in your SIMD code, you can get significantly faster. And finally, I'm going to show you measurements for chars, shorts, and ints. Okay, did we write a good strlen? Right. So my strlen here is called find unguarded, and this is standard strlen that comes with libc on Linux. We can see that on 40 bytes we're faster than strlen. I suspect mostly due to inlining. Then for 1,000 bytes, we're slower. And for 10,000 bytes, we're even slower, like significantly. We are 2 times slower than standard strlen. Why? Well, the thing is that the way we wrote that code is using just one 32-byte registers. But we have a few of those, and we can utilize hardware parallelism to make it faster. So let's just unroll, right? If you see when we unroll the 40 bytes, the green one is unrolled one, right? The 40 bytes is roughly the same. For 1,000 bytes, let me remove this one, we're a little bit faster than the standard strlen, and it's actually going to be even faster if I go to smaller size. And finally, for 2,000 or for 10,000 bytes, I'm slower than standard strlen still. Why? First, let me say that this is actually my find unguarded implementation. I like this one better than what we're going to do next, because I believe that smaller sizes are more important than large sizes in general case. In case of strlen, how often do you need to strlen 10,000 bytes? That's unreasonable. However, for regular find implementation, just std find like algorithm, I use a similar technique to what strlen does. What they did, they use multiple registers smarter than just unrolling. Let's say I'm going to load 4 registers worth of data, right? And then I'm going to test all of those 4 registers, and I can utilize hardware parallelism just basically by writing them one after another to do that in parallel. So it will take like one cycle to do all 4 tests. And then I'm going to do an OR, another OR. And finally, I'm going to check, hey, was there any zeros in there? So in this way, in 1, 2, 3, 4, well, maybe 5, any is a bit complicated instructions, we can actually test 4 registers worth of data. Let's see the measurements. So this is, find unguarded, and this is just regular find. For 40 bytes, it's a little bit slower. Because it needs to do the boundaries, like, find unguarded can just run for it, and find cannot. It has to check, hey, are we empty or whatnot. For 1,000 bytes, I honestly don't know what happens. I suspect this is some sort of measurement issue. However, for 10,000 bytes, we see that we have the same performance as standard strlen, like even a little bit better. So kind of our optimization works. And then actually, if you look at code of libc strlen, it will look very similar to what I just described. But it was not really interesting to beat standard strlen. Like strlen is great. The question is, can you do this when you actually don't have a strlen? When you need to find something else? Okay, so let's compare with scalar code. This is unguarded, so this is like strlen, no boundary check. For chars, we're about 17 times faster. For shorts, we're about 4 times faster. And for ints, we're about 2 times faster. And this is on 40 bytes. So we search integers, 10 integers, we search 2 times faster, right? And for 1,000 bytes, this is about 30 times. For integers, this is about 9 times. And same dynamic goes for 10,000 bytes. A very similar picture you can observe for regular find with boundaries, where you don't know that you're going to find the element. Like, you know, this is going to be 9 times, trust me. Yes, 10 times, because we're doing a different approach. I will also advise to look at performance depending on type. And we see the things that I told you about, that SIMD doesn't care about your type. You have 32-byte registers, and you do the same thing. A couple of notes. First of all, huge thanks to Stephen Cannon on Stack Overflow for explaining how strlen works. And the second thing is, int has to be aligned to alignment of int. This is a generally rule for C++. You have to respect your type alignments. Like, if you have a type and it has an alignment requirement, it has to be you have to adjust it, and the compiler will rely on it heavily. But and if you write regular code, it will always be the case. However, if you do reinterpret casts or whatnot, that might not be the case anymore, right? You just override the numbers, which is, fine. But if you want to speed up, look up for 4 bytes just 4 bytes from random places, still doable with SIMD. You just need to structure it differently. Okay, and with this, I'm ready to jump into some other algorithms. The first algorithm we're going to discuss is reduce. As I mentioned before, reduce is one of the algorithms that compiler can do for you. Generally speaking, you never should really write a reduction by hand. However, it offers a couple of useful insights into how that works and how you can write SIMD code. There are 2 fundamental cases. Imagine that you add up chars, right? If you add up chars, you will get overflow really, really quick, right? So you want to add to some different type, you want to add chars to, let's say, an integer, right? And this is going to be our second case. And the first case is going to be when we add types to the same type. This can also be useful. If you add integers, you don't expect to overflow. If you, let's say, use a min as your reduction operation, perfectly valid to do to the same type. We'll need a couple of primitives, right? First of all, we'll need replace ignored. Basically, you have a register, you have some elements you want to ignore, and you override them with a different element, right? And the second thing we'll need is reduce wide. Basically, you have a register, and you want to compute the sum of that register with the reduction operations that you have. Okay, let's see how it works. This is my interface to reduce. This is first, last, operation. Operation is a vector operation. So if you have an addition, it has to be add a register of integers to a register of integers. And then there's 0, and 0 to this operation. This is where I differ with the standard interface. The standard interface allows you to pass any initial value in here. I insist on it being 0. I will show you more in the end. One thing I didn't mention, reduce is C++ 17 version of accumulate. And the reason it exists is because this operation is required to be commutative and associative, and we'll also see why. So, okay, let's say I have my array. It's somewhere in memory. I have 4 registers of running sums. This is sums, this is sums, this is sums, this is sums. First, I'm going to align my F, I'm going to load a register, and I'm going to replace everything here with zeros and add it to the first running sum. And, the second register, I'm going to add to the second register running sums, etc. Then I'm going to add them all together. And finally, using my reduce wide primitive, I'm going to compute an overall sum. You might notice that we add elements into this running sums in a completely random order, effectively. And this is why we really need this operation to be commutative and associative. Okay. In this talk, I'm not talking about how to do things with intrinsics directly, like we're not going into that. But I'm going to explain how reduce wide works, because it's more about algorithms and less about intrinsics. Let's say I have my register, like A, B, C, and D values. What I'm going to do is I'm going to split it in half and move things around. This is, there is primitives to do it. Like you can do it in one instruction. I'm going to add them together and get A plus C, B plus D, A plus C, B plus D, right? And then I'm going to shuffle each half again. And this way, when I add them, I'm going to get A plus B plus C plus D. So exactly what we expected. Cool. A second algorithm we're going to look at reduce is the case when we want to reduce to a different type. So again, we want to add our chars to, let's say, a short. For this, we will need, first we'll need this primitive of y, t, and n. Basically, if you just write if wide, it will select the default register size for you, for your platform. But we can say, but actually it will support emulation of arbitrary size. So you can, arbitrary power of 2. So you can have, let's say my native size is 32 characters, but I can create a register of 16 characters, and if will do correct things for me. And the second thing I need is convert primitive. What it takes is it takes 16 characters, wide of 16 characters, and we'll convert it to wide of 16 shorts, sorry. Let's see how that works. So the same as before, this is my array, and let's say this is chars. And I want to add them to shorts, and this is going to be my running sums, same as before. But now this is going to be, each one of them is going to be 16 shorts and not 32 chars. And what I'm going to do next is I'm going to load, instead of loading 32 chars at a time, I'm only going to load 16 chars at a time. And then convert them to 16 shorts, and then add them. Right? This way, I can avoid the overflow and do the computation correctly. There are a bunch of ways to do this, but if you actually look at what your Godbolt and what Clang does for your reduce, this is exactly what it does. Okay, let's see the numbers. There are, because this is reduce, and reduce is generated by a compiler, we don't really have a scalar baseline. So there are two interesting things to see here. One is that, like in the end, compiler and I have exactly the same performance on sufficiently large size. Also, that if you add chars to chars, and if you add chars to shorts, and if you add chars to ints, you're going to have different performance, which is very expected because, like when we add chars to chars, we can do 32 at a time. When I add to shorts, we can do only 16 at a time, and to ints, we can only do 8 at a time. Second interesting thing here is that on very small sizes, and this is consistent between 40 chars and shorts, my implementation is faster. Why? The thing is that we do this ignore thing. So we load the register and we replace elements we don't want with zeros. And compiler will do scalar cleanup. It will add one by one, elements until it gets to the point where it can get vectorized. For reduction, my method is faster. Okay. So this is for shorts, same situation, and for integers. The next algorithm I'm going to talk about is inclusive scan. Inclusive scan is a C++ 17 version, same as reduce, but for stud partial sum. And the difference with stud partial sum, again, is that you are required to provide it commutative and associative operation. Technically speaking, in inclusive scan, you can pass an arbitrary output iterator, right? So you can, go through one array and write results into a different array. However, like for the sake of simplicity, we're only going to do an in-place version. So basically, we're going to overwrite elements in place. We will need a couple of primitives. First of all, we need store. right? And again, we accept a pointer, a register, and whatever bits of that register we want to not write there. And second thing we need is this inclusive sign wide, which is similar to reduce wide. It will compute a partial sum of our register, right? So let's see how it works. This is my interface again. First, last, our plus operation, and the 0. And here it really has to be a 0 for this operation. I don't see a way around it. So same as before, we're going to have our array. We're going to have an aligned line F. Load the register from there. Everything that was ignored replaced with 0. Then what we're going to do is we're going to compute a partial sum of this register, right? In case of just first register, we can just write it back. It's okay. However, like when you do the next registers, you also need to have all of the sum before, right? And this is going to be all of my sum before, and then I'm adding them together and writing this result there. And finally, I need to update my running sum with the last element I just wrote, which is going to be equal to the sum of all the previous elements. Same as before, let's look at inclusive scan wide as an operation on a register. This is my register. It's going to be 4 values, A, B, C, and D. What I can do in like one instruction is I can put a 0 in first element and shift all of the elements to the right by 1. And then, add them together. What I get is A plus B plus C, and C plus D, right? And then if you look at it carefully, like you can see that the result that we want is actually to add the left half to the right half. So we can do, again, 0, 0, A plus B, add them together, and we're going to get what we want. So A plus B plus C, A plus B plus C plus D. In this case, right, you see what we're doing scan on every register. So the speed up we expect, unlike the previous cases, is how fast we can do this scan compared to the scalar version of the same scan. And so we need to understand this operation turns out to be logarithmic because we have 1 0, and then we're going to have 2 zeros, right? This is logarithmic. So we expect, because we have like 32 chars, we expect about 5. We expect about 4 for shorts. We expect about 3 for ints because we have 16 shorts and 8 ints in one register. Let's see the numbers. Unfortunately, for 40 bytes, using SIMD here is a pessimization, right? And the reason is actually that this partial store that ignores some part of our register is expensive. Like I tried really hard to make it less expensive, didn't work out. However, for 1,000 bytes, we get really close to the picture we wanted. So we are about 5 times faster for char. We're about 3 times faster for short. We wanted 4, but okay. And we're about 2 times faster for int. And similar picture for 10,000 bytes. Okay. Couple notes on inclusive scan. First of all, huge thanks to Zbazan from Stack Overflow for explaining how to do this inclusive scan thing on a register. Second thing, I don't talk about intrinsics, but I'll mention this one. There's an intrinsic called mask move U. Avoid it like a plague. It is really, really slow. And the final algorithm we're going to cover is remove, right? Remove is basically you mark all of the elements you want to remove and everything else is stored to the left. The key to understanding how to do remove with SIMD is this compressed store operation. Well, what is it? Let's say I have a register and I have a mask. And everything that is marked with true, I want to keep. And I have a pointer as well. And what this will do in a few instructions, it will pack all of those values that I selected into memory in one place, right? So this is going to be B, C, F, J, K are going to be written. And then it's going to return me where it stopped. So we kind of already can see how we can do remove because we can, compress the first registers and compress the second register, etc. There are two variations that I have here. One of them is unsafe, and the other one is precise. And the difference between them is that unsafe version can write some extra garbage on the end, and then the next iteration we're just going to overwrite it, and then we're going to be fine. And the precise version, will not do it, but it's more expensive. Okay, so what we will need? We will need this compressed or unsafe thing. We'll need compressed or precise. Actually, just for convenience, if you pass some elements to ignore in compressed or unsafe, so you don't want to acknowledge some of the element, it will just do precise, and that works out nicely. Then there is if not helper. Basically, compressed or unsafe, it will store everything that is marked as true. But what I actually want to do is store everything that is marked as false. And no problem, you can invert this logical thing. But it is better if I do it for you. So if you pass this if not around logical, it will invert the logical inside the operation. Well, this is kind of helper. Okay, let's see the operation. It's very similar interface to the standard one, first, last, and test, which returns me, booleans that I want to remove. So this is my array. I'm going to load the first register, same as before. Everything here is ignored. I need to keep track of where to write. There are a couple of choices you can make here. On one hand, you can put it as aligned F, same place. On the other hand, you can put it where F is. My recommendation is to always keep the pointers, if you deal with parallel arrays, or in this case, one array, but we write and read to it, keep them as parallel, right? This way, the code will roll off much nicer. So we're going to load our first register, we're going to test it, and we're going to, store other elements we've had. And then we update our out and do the same operation on the next register. Let's see the measurements. So for 40 bytes, none of this makes sense. Standard remove beats us. However, if we go to 1,000 bytes, the situation is much nicer. Let me explain the benchmark a little bit. I am deleting zeros from array. And basically, the axis here is what the percentage of zeros in array is. Here it's 50%. Here is no 0%. Here is 5%. We can see that the scalar code is heavily affected by branch prediction and what data we have. And so whereas we have 50%, we're about 25 times faster than the scalar version of the same code. A similar case here on 10,000 bytes. For shorts, it's similar situation on 10,000 bytes. On 1,000, there's something happening here. I don't know what. And for integers, again, something happened. I'm not sure, but kind of the general dynamics that scalar code depends on branching and SIMD doesn't. SIMD doesn't, because effectively what you do is you do the same operation over and over again. You just do some computation and write the results. There are no branches, right? Which is really nice. So what do we get here? For 5%, we're about 4 times faster for integers, right? Here for shorts, I don't know. We're about 2 times faster. Or for 10,000 bytes of shorts, we're about 10 times faster. So speed up is crazy. I would also point out, you might think, hey, when do I need to remove half of my elements? This is uncommon. But actually, if you think about sort, you do a partition, and this is effectively what you're doing, right? You remove half of your elements, or roughly half of your elements. So this case is very important as well, as much as this case. Okay. So a couple of notes on remove. First of all, huge thanks to Peter Cardes for explaining on Stack Overflow on how to do this compressed store thing in AVX2. This is very much a non-trivial thing. Second thing is I'm going to rant about remove copy. Basically, there are some algorithms like remove copy, partition copy, copy if, right? And they all have the same interface, first, last, and output iterator, which is awesome for scalar code, nothing more is needed. However, for SIMD code, if you don't tell me how much space you have in the output range, I effectively can never use compressed store unsafe, because you can, pre-compute the elements, and maybe the next register will never, maybe this is the last elements we're going to write, and you pre-compute the exact size that you want. So for student-seek, unfortunately, they haven't changed this interface, and this makes this particular algorithm slower. A few general notes. Massive speedups. Like we saw 10 times, even 5, 10 times, even 2 times is a really nice speed up. And I understand this is complicated, right? And it really is. Like writing this code is not trivial, but I think that for performance critical code, it's important. I mentioned code alignment, right? The thing is that code alignment typically depends on branches. Right, so if you have the branches close together, the code alignment effects will be much more visible. However, SIMD code, especially very unrolled one, tends to have like giant blocks of code with no branches whatsoever. So code alignment impact is very minimal. It's nice. You don't really have to worry about that much. We saw with remove, we saw this kind of impact of data on SIMD is minimal. Like you don't care which data you have. It is not always the case, but much, much more the case with SIMDs and what scalar code. Awfully nice. Aligned and aligned memory access. I specifically didn't focus on it because it's not that important. In this talk, the only place we used unaligned memory access was in compressed or unsafe. Everything else was aligned. Generally speaking, I have some experiments with aligned, unaligned access. But basically, if your address is not aligned, you should use different instructions if you're aligned. However, in terms of instructions, at least on my machine, there was no performance difference whatsoever. I read online that what the problem is that you can get is that you have, let's say, 64-byte cache line. And if you read unaligned, you can read somewhere in the middle of that. And so you reduce the utility of your cache lines like 2 times effectively, right? Because you read like, instead of using 64 bytes, you only use 32. I don't know. That's what they say. But however, I will mention that unaligned operations are really important if you have 2 ranges. Whereas you have no escape of doing unaligned. What didn't I cover? Multiple range algorithms. It's totally doable. I have some sketchy implementation of strcmp. str is a thing. You name it. But just I wanted to show you. But I have very limited time. Partition. You can do actually. We kind of understand how to do partition copy. Hopefully, because we have this compressor unsafe, and we can compressor here, compressor here. Nice. You can actually do it in place. So you can do complete quicksort with no allocation using SIMD. Really cool. You can do reverse of the algorithm of an array with SIMD. Also really cool. SIMD is often used to do some floating point and some math. Absolutely doable. I just wasn't interested, but this is a main use case for many people. Cache effects. Like for most part, even the biggest size I measured is 10,000 bytes. It's nothing in terms of cache size, right? Everything fits in L1 comfortably. However, the thing is, people notice that if you do SIMD, you massively speed up your computation. It means that sometimes even the speed of your memory pipe is not fast enough to keep up. Even if everything is perfectly prefetched, just you don't get data fast enough sometimes. And so people do crazy things like some compression of memory access and stuff. Very interesting papers, we didn't cover it at all. There are some ways you can basically, we talked only about arrays. You can actually gather in a SIMD register data from multiple addresses. I know that that's a thing. I have no idea how fast it is or how good it is. When looking at it, I was like, hey, SIMD is really powerful. I can do all of the things. Maybe I can do everything. Well, not really, right? For one thing, I don't know how to do merge and set union type of algorithms. Basically, when you need to decide which elements should go first, which are like shuffle based on your comparison, don't know how to do it. Maybe it's possible. I don't know how to do insertion sort or some equivalent of that. Like, we know how to partition, but in every sort you do, in the end, it's going to go, with some small operation. It would be really cool to vectorize that as well, and I don't know how. Operating on partial structs. What do I mean? Like, it's very common for you to write something like for each element in the pair, do plus plus to the second value or whatever. Right? If you do this with SIMD, you better write the whole pair in there. So you can load the whole pair, do your addition, and write it back. But you can't really not write to those elements. Yeah. Watch out, maybe that prevents some of your vectorization in your program. I don't know. Huge thanks to Joel Falcou for writing Eve library and being super supportive and answering all of my questions. And to Peter Cardes for answering like unreasonable amount of questions on Stack Overflow. If you practically Google anything on SIMD, most likely it'll be his answer. Links. So there is my code. You can find it here in Unseek Eve. There is the Eve library. Try it out if you have C++ 20. If you want to see some SIMD code, real SIMD code, there is a macOS implementation of libc. It's written in assembly, but has really nice comments. There is glibc. It's more complete. It's faster and no comments. Really hard to read. I have a bunch of Stack Overflow posts that I wrote while preparing for this. You can look at that. That talks about how to do compressed store, how to do partial stores. There are really cool series of blog posts on vectorized sort. I suggest you check them out. And finally, I found this channel, Chili Tomato Noodle. It explains how to do like a bit older SIMDs at what I showed you here. Like, and I find it useful. The only problem is it has adult humor, so see for yourself how you're accepting what that is. I seriously suggest that you write strlen. Like, just from intrinsics, write strlen by hand. Questions? We have 5 minutes, I think. I'm going to log into Vimo. Sorry, one sec. Okay. I don't know yet. You can educate. Can you share benchmarks we used? Absolutely. If you look at my library, like it is there. Is the SIMD algorithms open source? Yes. Everything written with Eve. The problem is it compiles with, you need IVX2 for it. So you need IVX2. We're talking with Joel about upstreaming it to Eve directly, and then maybe like it will be available cross-platform, which would be really cool.